Hi everybody, so set 83 is a kind of subset of problems called coin problems. And what's nice about these coin problems is that we're going to use systems of equations to solve both of these problems. So let's take a look. In the first example, we have Jack and Betty. They have 28 coins that are nickels and dimes. If the value of the coins is $1.95, how many coins of each type do they have? Well, if we take two variables and we designate them as each coin, that's going to help us get started. So what I'm going to do is I'm going to let x equal the number of nickels and I'm going to let y equal the number of dimes. And what do I know about these two things? Well, I know that when I add x and y together, there's going to be a total of 28 coins. Now, another thing that I know is that when I add the total amount that each is worth together, I'm going to get $1.95. Now, how do I figure out how much each is worth? Well, for the nickels, I know that for every nickel I have, when I multiply it by 5/100ths, that's going to tell me the dollar value of those nickels. And for the dimes, I'm going to do the same thing, except it's going to be 10 cents times y. And when I add those together, it'll be $1.95. So now I have a system of equations that explains each of these constraints from the problem. And that should be enough that we can solve for x or y. Now, we can use any of the systems that we have. We have a few different strategies, for solving systems of equations. We've got elimination, substitution, and we do have graphing. I'm not going to use graphing because of the decimal values here. But what I'm going to use instead is I'm going to choose to use substitution. So I'm going to start with this top expression or top equation up here. And what I'm going to do is I'm going to solve for x. To be x equals 28 minus y. And what I'm going to do is substitute that into my next equation. So let me just put it here. I'm going to distribute my 5 cents. So I get $1.40 minus 0.05 y plus 0.1 y equals 195. I can combine like terms here. Okay, so I've got y is equal to 11. And so if I know that y is 11, then that's enough for me to substitute into the other one. I think I'm going to go for that top one now. So I know that x plus 11 equals 28. So that means that x has to be 17. So in the end, when I answer this question, we are going to have 17 nickels. And we are going to have 11 times. Okay, so let's look at the second example. And by the way, for that first one, you could totally have used elimination as well, and you would have been able to get the same result. John has $4.45 in quarters and dimes. He has 8 more quarters than dimes. How many coins of each type does he have? Well, we are going to, again, let x equal number of quarters. Guess not again, but we're going to designate a variable for each type of coin again. Y equal the number of dimes. And let's write some equations that are expressing what's going on in this description. So we know that it's $4.45 in quarters and dimes. Well, if we know the number of dimes, we can multiply that by 0.1, add it to the quarters, like so, and when we do that, we'll get $4.45. Okay, 8 more quarters than dimes. So however many quarters we have, or however many dimes we have, we could say, when we add 8 to that, that will equal the number of quarters. That will equal x, like so. Right? 8 more quarters than dimes. So we know there'll be more quarters. Yeah. Okay, good. So now that I've got my system set up, we can solve using substitution or elimination. I'm using substitution again. My bottom one is already solved for x. So what I'm going to do is I'm going to substitute that y plus 8 into the x on the top equation. And here we go. Okay, so I got y equals 7. That would mean our number of dimes is 7. And then if we substitute that into the other equation, that would mean 7 plus 8 equals our x value. So x would have to equal 15. So in the end, to summarize what we found, we've got 15 quarters and we've got 7 dimes. So this set addresses multiplication of radicals as well as looking at functions and defining functions specifically. So what's really nice about multiplying radicals is that if you know that you can change the order of multiplication, which you can because of the commutative property of multiplication, and you know that you can multiply radicals together, this should be kind of intuitive. So if you look at this first one, I've got 4 root 3 times 3 root 2. So what I'm going to do is I'm going to kind of change the order, and you can do this in your brain. You don't necessarily have to write it out like I'm doing here, so that you can multiply the radicals together, and then you can multiply the non-radicals together, right? So you'd get 4 times 3, which is 12, and root 3 times root 2, which is root 6. And I always like to do a quick check to make sure that I can't simplify what's under the radical symbol, like with the 6. That would only break down to a 2 and a 3, so that's all I can do. And by the way, you can always plug what you started with into your calculator and see if you got the same thing as what you ended with. So let's do the same thing down here. I'm going to multiply 4 times 6, which is 24. I'm going to multiply root 3 times root 6, and I get root 18. With this one, I am going to have to do a little bit of simplification of the root 18, as we've done before. Recognizing that I can pull out a 3 and leave a 2 inside. So 3 times 24 is 72. And then leave that 2 inside to get 72 root 2. So we can also distribute these, as is this last example here for the multiplication of radicals, right? We have 4 root 3 times the quantity, 5 root 2 plus 6 root 6. So what I'm going to do is I'm going to distribute that 4 root 3 over the 5 root 2 and the 6 root 3. And what I would get is 4 root 3 times 5 root 2 plus 4 root 3 times 6 root 3. So what can I do over here? Well, I've got 4 times 5 is 20. Root 3 times root 2 would be root 6 plus 24. Root 3 times root 3 is root 9. At this point, you can recognize, oh yeah, we actually can square root 9 to get 3. So 3 times 24 is 72. And what we end up with is a 20 root 6 plus 72 would be an exact answer. All right, let's talk about definitions of functions. So a function is a specific relation where every x input can have only one output, or y, and 2 inputs can have the same output. So if you go into your book, there's kind of these bubble diagrams that look like this, right? Where they have kind of the domain and range represented in these bubbles with arrows. So I'm going to demonstrate kind of how one of these looks, a function situation. And then there's a few other examples that you can look at on page 348 and 349. So here's kind of your most basic kind of function example, is that if you have a domain that includes numbers like 4, 2, and 1, each of these could be thought as inputs, and they could be paired with a unique output in the range, right? Because we know that the domain kind of goes with the x inputs, and the range corresponds to the y. So this is an example of a function, because for each of these inputs, it's just there is one unique output for each of them. The second part of this says 2 inputs can have the same output. So one of the examples that you can see in your book for this is a situation where you got the domain and range bubbles, right? And the domain is 4 and 2, and your range is 3, and each of these can have the output 3, but they still each only have 1. And so it's very important that you recognize that these are functions. Now, an example of one off the top of my head that would not be a function, so these are both functions here. Something that would not be a function is where you'd have your input, like 4, going to 2 different outputs. This would be an example of a situation that is not a function. And the reason for that is because the 4 has 2 outputs, 6 and 7. So what I'd like you to do now to finish this up before you go to the problem set is to actually look at pages 348 and 349. And there's a bunch of situations explained to you that are functions and non-functions before you keep going.